Okay, in this video, we're going to consider just some basic examples of hyperbolic integrals, just to kind of get warmed up to the subject, and then we'll have some future videos where we tackle problems that are a little bit more complicated. For the first one here, we have the integral of the hyperbolic tangent squared of x dx. And here, if we remember one of our basic formulas for hyperbolic functions, we know that this is the hyperbolic secant squared of x minus 1 dx. So we break up into two integrals, and for the integral of the hyperbolic secant squared dx, hopefully you recognize that right away, because the differential of the hyperbolic tangent of x, that is the hyperbolic secant squared x. So the integral of that would be the hyperbolic tangent of x minus this integral, that's minus x, and plus an arbitrary constant of integration, this then would be the solution to that integral. Now, instead of having the hyperbolic tangent squared of x, suppose we had the hyperbolic tangent of x. Now, if we think of it in terms of its definition, that's the hyperbolic sine of x divided by the hyperbolic cosine of x dx. So if we say let u equal the hyperbolic cosine, then du will equal plus the hyperbolic sine of x dx. So this would be equal to the integral of du over u equal the natural log of u, which is this, so this would be the solution to this integral. Now, the hyperbolic tangent of x, if we didn't write it out like this, suppose we wrote it out in exponential form like this. So let's look at this integral for a minute. If I called this u, then du would be e to the x minus e to the minus x, which is what this is right here. So saying let u equal this, then du is, and this would be minus e to the minus x, which is what our numerator is, so this will become the integral of du over u, which would equal the natural log of e to the x minus e to the minus x, plus an arbitrary constant. Now, here we said it was the hyperbolic cosine. Here we don't quite have that, do we? But actually, these two expressions are the same, and the reason for that is, let's look at this one and write it out. That's the natural log of e to the x. This is the natural log of u, which is this plus here. Not this one, this one. We get the natural log of u, which is this. And here, this definition is e to the x plus e to the minus x divided by 2. That's what this is. and this equals the natural log of e to the x plus e to the minus x minus the natural log of 2. But here we have an arbitrary constant, and we can put these together here into a different arbitrary constant, and that's what this is. So these two expressions here indeed are equivalent due to the property of natural logarithms and the fact that we have arbitrary constants here. So those weren't too difficult, just trying to recall some basic ideas here is all. What about this one here, written without a dx? There, now it's a proper integral. And let's see, we know that the hyperbolic cosine squared of x, that's equal to 1/2 the hyperbolic cosine of 2x plus 1. So this here would be equal to 1/2 the integral of the cosine of 6x plus 1 dx. And the integral of this, that's the hyperbolic sine of 6x divided by 6. We have a 1/2 over here, so that would be 1/12 that. And then from here we have plus 1/2 x plus an arbitrary constant. So this would be the solution to that integral. Again, there's no tricks involved here. We'll just kind of recall some basic things, kind of get us warmed up till we might face some more complicated type of integrals. And finally, we have this one to look at. Here we have integral of the hyperbolic sine of a square root of x divided by the square root of x. And here, we don't see much else we can do. Let's just try and express this in terms of its basic definition. So this will become the integral of e to the square root of x, subtract e to the minus square root of x, divided by 2 times the square root of x dx. Almost like the only thing that we could really attempt to do right now is to see if a u-du type substitution works out. Let u say equal x to the 1/2. So then du will equal 1/2 x to the minus 1/2 dx. Now what we're going to attempt to do then is express the integral not in terms of the variable x, but in terms of the variable u, which means that for dx, we want to have this expressed in terms of the variable u. So first of all, let's get this on this side of the equation, and that will give us then two times x to the plus 1/2 times du equals dx. Okay, so x to the 1/2, though, that's u, so we're saying 2 times u du equals dx. So now I have, this is in terms of u, That will be in terms of u, and so will this. So let's see how we can rewrite this integral. We're going to have integral e to the u minus e to the minus u divided by 2 times u. Now dx, that's equal to 2u du. So now we're going to have times 2u du. These cancel, and we have this. The integral of e to the u, that's e to the u. The integral of e to the minus u, and that's going to be minus e to the minus u, with a minus sign before it. The integral of this is minus e to the u. Here we have a minus, so that makes this plus e to the u. And this equals, you can think of this as 2 times the hyperbolic cosine of u. But this is our substitution here, so finally we're going to get this will equal then 2 times the hyperbolic cosine of the square root of x plus a constant. So of all the ones that we considered, this one involved the most work. Again, we went back to here, expressed it in this basic form based upon the definition here, and not knowing what else to do really, we tried a u du substitution, saying let's just call the square root of x, call it u. So du is 1/2 x to the minus 1/2 dx. Get everything under this side of the equation. Now we want everything here expressed in terms of u, which is easy enough because of our substitution. So we have dx is expressed in terms of u and du. So we go ahead and make the substitutions. This is e to the u minus e to the minus u divided by 2u, and then dx, that's this. These cancel. Now it becomes simple, and the rest of it falls into place. So that's it. We just want to consider some basic examples. If you have time, come back and join us for some more videos, and we'll try to consider some more complicated examples.